Good afternoon, everyone. How are you? Good? Hopefully, you'll be good also after the session. And yeah, first of all, thanks very much to making it here. I know MGM is quite far from the rest, so already 10 points for every one of you to make it here. At least we are not alone, which is great. My name is Adrian Hornsby. I'm principal engineer with the AWS reliability team. We own the Fault Injection Service. It used to be called Simulator, but 15th of November, we renamed it to Service to make it a little bit easier to understand. I'll be joined by Iris, who is a senior product manager in our team. She'll talk a little bit about today's announcements. If you haven't seen today's announcements, we've launched a bunch of scenarios to test multi-AZ applications and multi-region applications, and she'll be diving into these ones. So before diving into these, I'd love to talk a little bit about the why of resilience and why are we launching those scenarios today. And I'll start by asking a simple question. What is a little bit the price of downtime? Does anybody have any idea a little bit? How much does this cost, roughly? Right? It's expensive. What? It is very expensive, millions of dollars. Actually, the recent surveys say that about 91% of enterprise, for 91% of the enterprise, the cost of 1 hour of downtime is roughly $300K. And for 44% of those enterprise, it goes up to $1 million. And then for 18% of these one, it exceeds $5 million. If you've never thought about the cost of downtime, a good average is typically $10,000 per minute of downtime. It's a lot more expensive than you'd think, but when you are down, actually, there's a lot of implication, and we'll talk a little bit about that. Another very interesting number is that if you experience downtime regularly, your costs are likely to be about 16 times higher than a company that is not having as many downtime. All right. So it's pretty scary, and it's really easy to understand why downtime is something that people are worrying about in a company. And there's a lot of implications of downtime. Of course, your customers don't like it, but it's loss of revenue. It's typically can have an impact on compliance as well, which is something can be quite terrible to have. It can have an effect on the price of stock, and then also on the hiring process. And you just miss some businesses as well. But there's something a little bit more tricky here, is downtime also affect the brand, right? And it's a very famous quote that it takes a lifetime to get a good reputation, but you lose it very, very fast. And that's very, very, very common, especially nowadays where there's a lot of different application and competing businesses to get the attention of customers. Is if you have a lot of downtime, typically, your customers are going to go and try to search something somewhere else, and then it's very, very difficult to get them back to your platform. So downtime is very, very important. And it's challenging to avoid downtime. Actually, I would even say it's pretty much impossible to avoid downtime because we're dealing with complex systems. And people tend to think that complex systems is really related to very wide and big distributed system, but it's not really like that. In fact, I'd argue that even a very simple client-server application like this one is actually a complex system. If you think about it, there's a lot of possible permutations of failure. Like, for example, my client has to create a message, sends it over the network. The network needs to deliver the message to the server. The server typically needs to validate the message, maybe update a state in a data store, creates an answer, puts it on the network delivers that to the client validates and maybe also updates its local state. So there's tons of things that can go wrong here. Your network can become slow, you can have some latency, you can have some packet loss, your validation mechanism might fail, throw an error, your data store might be congested, right? It might be there's too many open connection and you can't write, so there's a failure, and so on and so on. So the permutations of failure in even this very little system is actually quite staggering. So if you think about this, when you build actually a quite wide distributed system in the cloud or hybrid or whatever you're doing, it really is complex and there's a lot of possibility for failures. So the question is, how do you avoid failure? Well, you can't, right? If there's a summary for this presentation is you can't avoid failure. Failures are just gonna happen and everything will fail over time, like Werner often says, our CTO. So you might ask, how do we do this? How do we handle failure, or how do we, mitigate maybe the impact of failures? And there's a very interesting book that's been written and called Resilience Engineering in Practice. And the authors break down resilience in 4 pillars. The first is anticipation, monitoring, responding, and then learning. So anticipation is, trying to come up with all the failure scenarios and try to think about the designs to have a resilient system. Then you have monitoring. Well, that's understanding what happens during a failure scenario. I'm pretty sure many of you have experienced an outage where you didn't have the right alarms or right monitoring. And then, in hindsight, you say, okay, maybe we could have done something. So monitoring is very important. And then you have responding. So responding is trying to understand what you have to do to recover from the failure. And this is not trivial. Sometimes you have very complex systems where you have to have a sequence of events, bring back your tier 0 application, tier 1, 2, and 3 in sequence. Sometimes, you realize that one system depends on the other, and it's down. So you end up with a circular dependency. This is quite problematic. So these are things of resilient systems as well. And then you have learning. Learning is sitting down after the outage and try to understand what happened, making sense of it, and derive best practices, and hopefully share them with the rest of the organization so everybody can learn out of it. So this is a very good way to think about resilient system, because a lot of time we tend to think about resilient system only as the technology itself. But there's the entire spectrum of the culture, the mechanisms, and the tools involved here. And so we took these 4 cornerstones of resilience, and we thought about how we've done resilience also at Amazon and AWS, and how our customers are doing it. And we've come up with something called the Resilience Lifecycle Framework. And basically, the lifecycle framework is a continuous resilience process by which you go through these steps and then try to understand, how to improve your system resilience. And it starts with setting objective. It sounds pretty trivial, but a lot of times we don't really understand why we want resilient systems, or what are the objectives, the business objectives. Is it resilience, the 4 nines of availability? Is it for live events? Is it a new feature? So why do we need resilience? And then we go and design and implement, right? And then evaluate and test, observing, respond and learn. And then it's a life cycle. What's interesting is if you look in a company, teams might be at different level of this life cycle. Some might be very deep, some might be just starting. And you might start somewhere. It's not always the case that you start with objectives. Sometimes you test because you've had a problem and you need to start thinking about it so that it doesn't happen again. And then the discussion and trying to fix it typically gets you into the conversation around setting objectives. What I'm trying to say is you can enter this life cycle at any time. You can access this lifecycle, by the way. We've published this into our documentation. So today, this presentation will focus a bit more into the design and implement and evaluate and test. So arguably, the most important part of designing a resilient system is to think about false isolation boundaries. Remember what I said, failures are going to happen. So you have two strategies to recover from failures. First is being able to recover very fast. So practice recovery. But the second is minimize the impact that you have on your workload. Try to limit the impact on customers. And this is where fault isolation boundaries kick in. Fault isolation boundary is a little bit similar to bulkheads in a boat. So a boat, typically they have bulkheads so that if a part of the boat gets a hole, it doesn't fill up the entire boat. It fills one part of the boat. So the idea here is similar, is you're trying to think about your system in terms of domains of blast radius. And this has very interesting property because you can have isolation of your workload, containment of failures, but more importantly, because you have a very finite size of your boundaries, you can you can understand it. You can understand that particular boundary, test it, understand its limit, and then you can use that and replicate it horizontally if possible. So testability here is very interesting. The most common ones, obviously, and I'm sure it's nothing new here, the most common isolation boundaries that we use is a region and then availability zones. There are 32 regions globally and 102 availability zones. A region is typically three or more availability zones. An availability zone is the collection of data centers that are, have isolated power, communication, and networking. Typically, AZs within a region are separated by roughly 100 kilometers, but not far enough so that we can still have single milliseconds latency between AZs. And we do that because we want synchronous replication, in some of our regional services. So AZs are also very isolated from one another. They have different power systems, different networking, different cooling systems, and they can withstand issues like a tornado, a earthquake, a power outage, or things like this. So these are very common, most commonly used fault isolation boundaries that we have. If you want to use this, or the most trivial way of using those boundaries, I would say probably the scenario one is building a multi-AZ application. That's really where everyone should be starting when you start your journey into building resilient application. You typically start with having instances distributed or compute distributed across multiple AZs, a database that also has replicas or failover into another AZ. And if an AZ were to experience some issues, so if you have a deployment that, for example, impact an AZ, if there's a problem in some of the service, some grave failures, and you really want to isolate the traffic from this AZ, typically you would move the traffic from an AZ to another. We call that AZ availability zone isolation, right? And typically here in this scenario, the primary instance would be failing over to a secondary region, and that particular standby would become the primary. Another very interesting fault isolation boundary that we use a lot here at Amazon and AWS is what we call a SAIL. A SAIL typically is another way how we contain the blast radius of failures. And what is very interesting with SAILs is, for example, you take a multi-AZ application. And this is the same slide that I've shown before. And that's our SAIL. So this is really an instantiation of a service, and we put that in the SAIL, including the data layer. And then we typically take this cell, and then we replicate those cells horizontally behind a thin routing layer. Typically, that's going to be Route 53 with a domain name that can direct traffic to different cells. And typically, we assign customers to one or more cells, depending on the level of resilience we want to achieve. But here, if something were to happen in one cell, for example, if cell 1 example.com was to have a deployment failure, which typically deployments is very common to have issue, and we don't want that issue to happen to the rest of the cells. We do the deployment in the cell 1. We look how the cell behaves. If something bad happens, then we can take the cell out of the routing layer and then move customers to other cells. Or depending on how we route the traffic, typically customers will be assigned multiple cells. But this is a very interesting design. And it's also very interesting to use this sort of design in chaos engineering, because you can create a cell where you only have synthetic users, synthetic traffic. It's exactly the same size of the other cells that take production traffic and real users, so we can conduct fault, chaos engineering in one cell, understand the failure modes, improve its resilience, and then duplicate that to the rest of the cells. So that's a very good way we actually can do fault injection in a production environment, and Prime Video does something very similar to that. Another very important fault isolation boundary is something we call control plane and data plane separation. So the control plane is typically the operation by which you set up the resources in an account, and then the data plane is basically using those resources. So if you think about EC2 instances, for example, the control plane is start, deploy, start an instance. That's a control plane. The instance then is available for you to be used, and that's data plane operation. And we do this because control plane typically are a little bit more complicated. They have workflows, they have more database, they have more business logic. And in an outage, what we want is avoid using control plane. So we make data plane as simple as possible so that we can use resources that are deployed without having too much complexity. Because typically in an outage, control plane will statistically have more issues. So this is a very common design that we also have internally. That leads me to the concept of static stability. How many of you have used or heard the concept of static stability? Well, I have a few at least. That's great. So it's something we use very, very often here. And typically, we define a statically stable system when, if there is an outage, we don't do any control plane operation. So as I said, it means that our system is stable. I'll give you a very simple example so that what I'm saying hopefully will make sense. If you have a system like a plane with 4 engines, if the plane loses 2 of this engine and can continue flying without impacting its flight, the system is statically stable, right? So that, if you think about this when designing system, it gives you very interesting properties. So for example, if you start designing multiple AZ applications, so say you have 3 AZs, and one AZ experiences some issues, or there's some deployment, and your application in one AZ starts to fail. If the other AZs cannot handle the surge of traffic from this AZ that has some problem, then your system is not statically stable. If the other AZ, without doing any control plane operations, so without starting any new instances, if they can handle the traffic of the AZ that has issues, then your system is statically stable. And we think about this a lot when we design our systems, because as I said, during an outage, it's very common that control plane operation won't work. The last thing you want to do in an outage is try to start new instances, or try to deploy a cluster, or try to, typically you need to do nothing, and the system needs to handle the failure by itself. In that sense, then your system is statically stable. And this is a very, very important concept when we talk about resilience. We've wrote a very good paper around how Lambda use multiple AZ application to actually build its resilience, and they build their static stability using availability zones. So I highly suggest you to read this article, not because I wrote it with Marcia, but because it explains the concept with multiple AZ, which is very important concepts. Which leads me to the second part, which is evaluating and testing. Because, fault isolation boundary is great, but how do you evaluate and test them? And traditionally, actually, we've talked a lot about fault isolation boundaries, but it's been quite difficult for customers to test those fault isolation boundaries. You were left trying to do it on your own and things like this, which is not easy. So a few years ago, 2 years ago, I think, we launched a product to go and do resilience testing, which we'll talk a little bit about this. And resilience testing is really injecting stress in your system, observing and it responds, and then doing some improvement. And we do this to improve the reliability, the performance, the resilience of your system. But there's very interesting properties here. When you start injecting faults in the system, you really start to uncover hidden issues. Right? So for example, missing alarms, missing logs, missing observability. And it's better to observe this in a test environment rather than when it's in production. And what's also very interesting with resilience testing, it allows us to practice our operational muscle. I'm not sure if you often have outages, but systems are becoming more and more resilient. And I know that to become very fast at recovering fast, you need to have a really good muscle memory of operational practices. You know your command line, you know your run book, they are up to date. Everything needs to go fast. The last thing you want to do during an outage is realize that your operational procedures are outdated and they don't work, right? So injecting fault in the system is really good way to practice your operational muscle. And typically, when you inject fault in the system, you use something similar to the scientific method that we were taught at school, where you start with an hypothesis. It's like, what happened if I remove the database? Or what happened if I remove the authentication layer of my system? And then you go make an experiment to try to validate your hypothesis. Okay? If your hypothesis is, if I remove my database layer, my system will fall into a read-only mode and use cache and still continue working, then you go and test it. Until you test it, it's assumptions. And I can guarantee you assumptions, until you've turned an assumptions into a truth, your assumptions are wrong. Right? Or in assumptions you have at, let's say on Monday, on Friday, after 10 deployments, can go wrong. Right? Configuration drift, behavior drift. So it's important to regularly exercise these ones. So to go and test this kind of behavior, we launched, 2 years ago, we launched this Fault Injection Simulator, which we rebranded Fault Injection Services. And typically, that allows you to inject control experiment in your system. And to talk a little bit more in depth about this service, I want to invite Iris on stage and especially dive into these new announcement that we've done today. Thank you very much.
Thanks, Adrian. So in this next section, I'm going to dive into what FIS is, how to use it to test the resilience of your applications, And finally, probably my favorite part, talk about some new launches that we just announced today. Before I dive in, though, I thought we should go over some key FIS concepts. To start, to use FIS, you start with an experiment template that you set up, and when you run it, this creates an experiment. You can run an experiment template as many times as you want. Now, to set up the experiment template, you need to define a few key things. First are actions and targets. Actions are the actual faults you're injecting, while targets are the resources you're injecting the faults into. For example, if you want to terminate instances to simulate a loss of compute, your action would be terminate instance, and your targets are the EC2 instances you're injecting the faults into. You can specify targets with ARNs, or you can target by resource tags, which we recommend that you do when you're trying to target at scale. Next are safeguards and IAM controls. Using FIS is not about injecting chaos into your system. What it is running experiments in a controlled setting. And so with FIS, you can run safe, controlled experiments by stopping an experiment at any time manually, or you can use a stop condition, which is an alarm that you set up that, when triggered, will cause FIS to stop the experiment and automatically roll it back. The idea here is that you define the boundaries that you expect your application to operate within, and when outside of these boundaries, you tell the experiment to stop. Next, you also need to create an IAM role with permissions to allow FIS to take action on your resources. We recommend you use fine-grained permissions to explicitly define who can run an experiment, as well as what type of experiments they can run. And so these are the key FIS components, but we're always looking to make it easier for our customers to use FIS. And so So I'd like to mention a few of our new features. First, just a couple of weeks ago, we launched scenarios. We launched scenarios because customers have been telling us they know they want to test the resilience of their applications, but they just don't know where to start. We often get questions like, what application impairments should I be resilient to? And so this is where scenarios comes in. Scenarios are predefined actions and targets on experiment templates that are created and owned by AWS. For example, we have scenarios that allow you to check your application response to CPU load, such as increasing CPU load from 90% to 100%, or increasing latency on EKS pods. You can find scenarios from the scenario library in the FIS management console. And we also, just on Monday, launched support for multi-account experiments. And so if you have applications with resources spanning multiple accounts, you can now run scenarios on these applications from a single FIS experiment. And so we're excited to get these features out to you. Hope you get to try them and let us know what you think. This is kind of an overview of how these components work together. You can start from the AWS Management Console or the CLI with an experiment template where you define the actions and targets. The actions can be in any order, and you specify the duration of the actions. You should also create an IAM role with the permissions that allow FIS to take these specific actions. Once you start the experiment, you can view the effects of the experiment from your CloudWatch dashboard or monitoring tool of choice. The experiment ends when all actions have been completed or when the experiment has been stopped, such as via the stop condition. And once the experiment ends, you can view the results of the experiment and observe any performance, observability, and resilience issues. And once you gain confidence in your application response to the experiment, as well as the type of experiments you should run, you can set up the experiments to run automatically, for example, by using AWS FIS's Event Bridge scheduler integration, or by deploying these experiments into your CI/CD pipelines. So this is the end-to-end process of using FIS, which can be set up in minutes. Now, this is all great, but what can you test with FIS? We support a range of AWS services from compute, storage, networking, database, and management. FIS initially launched with support for EC2 instances, and this year we launched support for container faults for EKS pods and ECS tasks. So I want to mention that we have a fault to allow you to simulate unresponsive EBS volume, the EBS pause volume I/O. And this is an example of a unique AWS fault we launched, and we continue to look to expand both these types of faults. For example, just today, we launched 7 new actions across 6 new resource types, and we continue to look to expand both the services we support as well as the number of faults for each one. I also want to mention that with AWS Systems Manager's SSM doc and automation execution, you can inject custom faults into your applications. And AWS offers SSM documents to get you started, but it's a great way to self-service your own faults. And I also bring up our new actions because they're part of 2 new scenarios that we just announced today, as Adrian mentioned. These are our first complex multi-resource type scenarios that allow you to test not just components of an application, but an entire application across multi-AZ and multi-region. So I'm going to dive into a bit more detail on each one. Now, Adrian has already done a great job talking about the importance of building multi-AZ, and many of you may already be building applications in this way with replica hosts behind a load balancer across multiple AZs. But let's say there's a power interruption event in one AZ. How can you verify that you have the right alarms and monitoring in place to respond, and that your application can handle as expected in the remaining availability zones? This is where the AZ availability power interruption scenario comes in. This scenario enables customers to test the implementation of their multi-AZ architectures. It combines multiple FIS actions to replicate the symptoms of a power interruption in one AZ. The basic idea here is that when one AZ experiences a power interruption event, your application should be able to behave and perform as expected in the remaining availability zones. We include faults in this scenario that you would expect in a power interruption event, no matter how unlikely that is to occur. For example, EC2 instances and container pods and tasks are expected to fail, while load balancers and auto-scaling groups should be able to operate as expected. Region-based services such as Lambda should also be able to operate as expected as well. This is the current list of faults that we support at launch. It includes an action. First, it will stop EC2 instances, and as well as any pods and tasks on these instances. And we also have a new action to inject insufficient capacity errors into our auto-scaling groups and IAM roles to prevent any instance launch requests into the target availability zone. This scenario will also cause Elasticache and RDS databases to fail over. And finally, once the AZ comes back online, any persistent EBS volumes may be unresponsive. An end-to-end power interruption scenario of availability zone A would look like this. You would start your experiment targeting resources in availability zone A. This will cause compute to fail, and if you have any primary Elasticache nodes or writer RDS instances, those will fail over. Now, if you have the appropriate alarms and monitoring in place, and this scenario is a good way to test that, you should trigger your alarms and health checks. At this point, you should shift traffic out of AZA either with your standard operating procedures or with Route 53 application recovery controller's zonal shift which is an out-of-the-box capability of ALBs and NLBs that we particularly like because it's a good way to, because it's a good response to this type of scenario. And once you shift traffic, you can observe key metrics such as availability and latency to see how your application performs in the other availability zones. And once the experiment ends, you can fail over back to and see how your application recovers and verify that you can shift traffic back. Now, I'm going to show a pre-recorded demo targeting US FIS 1A on an application similar to this one, but with replica hosts in 3 availability zones behind an NLB. I've also already created synthetic monitoring on each of the zonal endpoints, as well as a regional canary that allows you to check the customer's experience during such a scenario. So to start, we'll start from the AWS FIS Management Console, which is under Resilience Hub. And you can find the scenario library on the left-hand side. So we'll navigate there. Next, you can see that we have a range of scenarios in the scenario library. And so you can select each one. I'm going to select the AZ availability power interruption scenario. And here is where you can see information about the scenario, including the exact actions and targets in each one. You can also see the actual JSON of the experiment template and copy it and modify it to your own needs. And finally, you can check out the details for any descriptions and additional documentation on the scenario. So I'm going to go ahead, create a template from this scenario. As I mentioned before, if you do have resources and multiple accounts, you can select this option here. I've already set up the app stack to be just in one account, so I'll go ahead and confirm. Now, as you can see, the actions and targets for this experiment are already defined here. So to set this experiment template up, what I need to do is just input a few key parameters. So I click on Edit Shared Parameters. Now, this is where you would specify the affected AZ. In our case, we want to target US FIS 1A resources, so I can select this parameter here. Next, so most resource types in this scenario we target with resource tags. FIS does not support targeting IAM roles with tags, and so we'll need to select an IAM role that we're injecting the insufficient capacity error to prevent instance launch requests. So I've created a demo role here that I'll select. And as I mentioned, we support targeting with tags. And this is where you would specify your tag key and value for each of the resource types. I've already tagged my resources accordingly, but you could use your own tagging convention. For instance, if you have a consistent tag for an application, you could specify that. And finally, you also need to specify the duration of the experiment. The default is 30-minute outage with a 30-minute recovery period. We don't have a full hour, so I just shortened it here. So now I don't need to do anything else when it comes to setting up the actions and targets. If I wanted to, I could click on a specific target and action just to see how the parameters have populated. So I've done that here just to show you. I'm targeting US FIS 1A as expected. And so next, if I wanted to, we have this experiment option that allows you to skip actions if you don't have a specific resource type in your stack. For instance, you don't have any Elasticache clusters, the experiment will simply skip that action. If I did want the experiment template to validate that I have all of the resources that are specified on this experiment, I could select fail, but the default for this option is that it'll skip actions. Finally, this is where you specify the IAM role that allows FIS to take actions. I've already created and set up the proper permissions, so I just select that here. But you would create one if you hadn't done so beforehand. I'm not going to specify stop condition for this demo because I do want the experiment to run all the way through, but if you had one, this is where you would define it. And finally, I think it's best practice to enable logs, so I'm going to just specify a destination S3 bucket to send my experiment logs. Finally, I can create a template from this scenario, and now I can run this template at any time. For this demo, I've gone ahead and started the experiment. Once I click start, the experiment's now initializing. So while it's initializing, I'm going to show the rest of the stack I have set up. As I mentioned, I have canaries in each zonal endpoint, as well as a regional customer canary, which is the FIS one. So have 6 healthy hosts behind my load balancer, 2 hosts in each availability zone. And as you can see here, my primary node is in USDIS-1A. For my RDS database, my writer instance is in USDIS-1A as well. So going back to the experiment, we can now see that the actions are in running or pending state. The RDS failover action has already completed because that just happens at one time. And so let's check out the impact of this experiment on the resources. So if I go to my auto-scaling group, I can see that instances are now being terminated in USDIS-1A. If I check the activity, I can see that the auto-scaling group did attempt to launch instances into USDIS-1A, but received insufficient capacity error that is injected by FIS. So that prevents the provisioning of instances into that target AZ. You can see now it's also deployed additional instances into the remaining availability zones. If I look at my load balancer, I also see a similar picture. I have only 4 healthy hosts right now. 2 hosts are currently initializing. The health checks are in an initializing state. And finally, if I check my RDS database, I do see that it's currently modifying. And I'll also go over to Elasticache cluster. It's also modifying, and the primary node has already failed over to USDIS-1C. Now I can check the status of my canaries. My canary is failing right now in USDIS-1A, but I also see that the regional canary representing the customer experience is also being impacted, so there are increased response times. And so this experiment shows that I'd probably want to improve my application, start a zonal shift traffic away from the AZ to be able to improve my application resilience and recovery time to this type of scenario. And so if I go back to the FIS experiment, I do see that my actions have completed. I did not have all resource types, so those actions were simply skipped. So hopefully that gives you a sense of how this type of scenario works. I'll now dive into details on our next scenario, which is cross-region connectivity. This scenario allows customers with multi-region applications to test that they can operate when their primary region is inaccessible. For most customers, a multi-AZ architecture is sufficient. But some customers have critical applications with extreme availability needs, or they have compliance requirements to show that they can fail over to a secondary region and prove that they can operate as expected in the secondary region. And so this scenario enables these customers to test if they have any hidden dependencies from a secondary region on a primary one, such as hard-coded regional endpoints, internal dependencies, and certificates. We include 4 new actions that we just launched today as part of this scenario. We have 2 new actions that disrupt cross-region network connectivity. This includes blocking cross-region connectivity from VPC, including VPC peering, API gateways, and cross-region AWS endpoints and endpoints exposed via load balancers. We also include a new action to pause any global table cross-region replication, and similarly, an S3 action that pauses cross-region replication from S3 buckets. You can also use this S3 action outside of this scenario to test, to be able to pause replication between buckets in the same region as well. So an end-to-end game day of a cross-region connectivity scenario would look like this. You would start the experiment in your secondary region, and this disrupts network connectivity and pauses replication. At this point, you can follow your standard operating procedures to shift traffic out of your primary region. And now you can monitor the effect of the experiment on your application. The default duration of this experiment is 3 hours, which should be sufficient to observe any impacts of this scenario. And you should watch out for any missing alarms or unusual behavior. And once you're confident in your application behavior, you can shift traffic back and see if your application recovers as you expect it to. Now, we're ending the end of our time together today. So we've talked about the importance of building multi-AZ and AWS fault boundaries and resilience best practices, as well as reviewed some tools available to you at AWS, such as AWS FIS. But if there's anything to take away from this presentation, building resilience across an organization really does take time. And so there's no secret sauce here, unfortunately, but building resilience is a habit and something everyone and every organization can achieve, but it just requires practice, practice, and practice. And so on that note, here are some resources for you to continue on your resilience journey. I'll pause here if there's any interest in taking pictures. And finally, thank you so much for your time today. We really appreciate you coming to spend the time with us here at reInvent. I know there's a lot going on, but if you don't mind spending a few more minutes to complete the session survey in the mobile app, and Adrian and I will also stick around for any questions out in the hallway on that side. So thank you so much.